what, tenths, hundreds, thousands, 10,000, 100,000s, millions. At the millionths position, we're off, right? Okay, so let's move a little bit further away. Let's go to cosine of, I don't know, let's go 0.3, and let's compare that to 1 minus 0.3 squared over 2. So what do you get there? Cosine of 0.3 is what? 0.9553. Good, yeah?
364.
364. Okay, we'll stop there. How about the next one? 0.955. Again? Oh yeah, 955. So they're matching up. You know, now we've lost some accuracy here, right? They're the same the first 3 digits, but after that we lost some, right? Here they were the same the first, like, 5 digits. And what's going to happen is as we get further away from 0, we're going to start to lose our precision. And what's really cool about this is if you were to graph this, look at this. This graph is really negative 1/2 x squared plus 1. That's really what it is, right? It's a parabola. It opens which way? Down, and it's been moved up 1. Agreed? So it looks like this. The projector I don't think is working, or else I would turn it on and show you this. But they're really close to one another. As long as you're near 0, these things are almost the same. And so if you're in a physics class or chemistry or whatever, if you're applying this and you get into a problem where you've got cosine appearing and then you have to do some sort of algebra or something to it, you can replace the cosine expression with this expression and it's good enough, right? Because in the real world, like if you're building something, you only have to be within a certain precision, don't you? I think I've said this before, when you're like manufacturing ball bearings, if you're manufacturing ball bearings for kids' tricycles, you don't have to be very precise about it. If it's for an engine, right, if it's for an aircraft engine, their tolerances have to be out to the thousandths of an inch, okay? This approximation is good enough for most applications. And you know what? If it's not good enough, I can do something to it. If you don't like that approximation, you need something more accurate, I'll just add this to it.
Oh, I see what you're doing.
And if I can guarantee you that this one right here, altogether, this 4th degree polynomial, will be even more precise. So now if you do this 0.3 and 0.3, and you do the 0.3 into here and there, they're going to be closer. Okay? So the big question is, where the hell did this come from? Right? Where is it coming from? Understand? So I'm going to still try and show you. We're not in the power series yet. I want to try and show you the idea. So let's say I'm trying to figure out a way to approximate cosine of x near 0, right? I'm trying to come up with something. And let's say I want to try and approximate it with a parabola. So I'm going to say, okay, I'm going to try and come up here with some function. I'm going to call it g of x. And I want it to be a parabola. So I want it to be like some constant plus some constant times x plus some other constant times x squared. So don't worry about the fact I wrote it backwards, okay? It's just a parabola written backwards, yes? That's a parabola, and I would like to know what's a sub 0, a sub 1, a sub 2. What are these constants that would get me a pretty good approximation of this? Okay? You all with me? All right. First, I could say, well, at 0, what is the value of this function at 0? 1. I would really like it if that's what that one gave me too, right? So if I plug 0 into this function, I really want 1, right? That's what I want. So how could you make that work? If that's 0 and that's 0, these are gone, right? That means that constant needs to be 1. Agreed? So just by that, I know that g of 0, which is a sub 0 plus a sub 1 times 0 plus a sub 2 times 0 squared, I need that to be 1, which means that a sub 0 is equal to 1. Okay? So far, that makes sense? Okay, so now here's my new function. this will get me at least the same value at 1. At 0. So what would be another thing I would really want to happen? I'd really like it if the slopes of the tangent lines were the same at 0. Right? Like the cosine function has a slope tangent line here of what? 0, right? It would be really nice if my function approximation had a derivative that was also the same there. So I can say, okay, what's the derivative of this? The derivative of this function is negative sine of x. And at 0, what is that value? 0, right? So I really would like this one to do the same thing. So let's take the derivative of our function. What's the derivative of our function? That's gone. That's just a sub 1 plus 2a sub 2x. Right? That's just power rule, so that derivative of constant's gone. This is a constant in front of x. Derivative of that's this, and derivative of that, power rule, right? And what do I really want this to do? Match up to that, right? So I want that when I plug 0 into this, I get, what, 0? But that means that a sub 1 plus 2 times a sub 2 times 0 must be equal to 0. This goes away, and what does that tell me a sub 1 needs to be? This a sub 1 needs to be 0. So now I've got a better function, right? So now I'll put my new one up here. My new one is 1 plus 0 times x plus a sub 2x squared. That's where I am, right? So what would be the next thing I would want? I wanted the function's value, this function's value at 0 to match that function's value at 0. Check, right? We got that? That's what the 1 got us. I wanted the derivative of this function at 0 to match the derivative of that function at 0. Got it to match, right? By making that 0. What would be the next logical thing? Okay, so first derivative gives you slope of tangent line. What does second derivative give you?
Direction.
Concavity. Would be nice if they had the same concavity, right? So why don't we make the second derivatives match? So what about the second derivative of this function? What's the second derivative of this function over here? Negative cosine x, right? And what would be the value of that derivative, second derivative at 0? Negative 1, right? Negative 1. So what I need from this is that when I take the second derivative of this, I'd like for it, when I plug 0 into it, to spit out negative 1. So now what I do is I take the second derivative of this. So the first derivative we already know is, what, 2 a sub 2x? Derivative of that. That's not even there, okay? And then this. Take the second derivative. What's the second derivative? 2a sub 2, right? And what do I want from this? When I plug 0 into this, I want it to be negative 1, right? Which means that 2a sub 2 needs to be equal to negative 1, which means a sub 2 needs to be negative 1/2. And now I've got a value for a sub 2, negative 1/2. And do you see why now 1 minus 1/2 x squared was a pretty good approximation? It's because it matches cosine. It matches cosine at 0, matches the value. The slopes of the tangent lines are the same. The concavity is the same. Now, as soon as you start stepping too far away from 0, things aren't going to match anymore, right? But I could keep going, right? Why not go make the third derivatives match? Well, what's the problem with that?
You're running out of variables.
If I take another derivative, I got 0, right? So when I started this, didn't I say, why don't I try and come up with a quadratic? Why not make it cubic? Why not make it 4th degree? Why not make it 5th degree? Why don't make it infinite degree? Why don't I make it a polynomial that never stops? An infinite series of powers of x, so that each derivative matches each derivative here. And if I do that, I love math. I'm getting goosebumps. Okay? If I do that, I have actually not created an approximation. I have actually created this function, but represented as a series, an infinite series of an infinite polynomial as opposed to a transcendental trig function. And that's what I think I've mentioned to you before when we started this chapter. This is all about taking functions we know and representing them in a different way. And then all the calculus and algebra and everything that you have done here can now be done with polynomials, which are so much easier to work with, right? Like if I had a polynomial, we can take derivatives all day long, right? All day long you can differentiate polynomials, right? I hope power rule just over and over. You can do that all day. You can integrate power rule all day long, right? If I take this right here, ask you to integrate it, you'll be like, no problem, right? No problem. I put this and I put x squared cosine x, you're done, you're cooked, you're toast. You can't do it, okay? You can't. But guess what a good approximation of that function is? X squared times 1 minus 1/2 x squared, right? That's a great approximation of that function. And so if I want to integrate this and go from 0 to 1, I just integrate that from 0 to 1. So much easier to work with. Does that make sense? So we are stepping into a very profound, big portion of what this is about. Now, the big kind of underlying question mark here is, if we are going to try and make an infinite series, we already know sometimes they converge and diverge. And so we have to be very careful about saying when this is a good approximation of this. Sometimes there are conditions, like, yes, this will work, but only if x is like certain values, or or sometimes we can say this will work for all the time. Okay, so we're going there. Okay, now we start the next section. Does that give you some small glimpse into where, like why and where and everything else? Okay, I hope so. When I stop getting excited about this is when I'm going to stop doing it, like talking about it. Power series, 8.5. I mean, think about that. Someone sat down and actually started thinking, I'd like to approximate this function, and just went through that exercise right there. Let's make it match at one point. Let's make the derivatives match. I mean, it's such a simple idea, but it leads you to it just blows the whole subject wide open with this whole concept of power series. All right, so here it is, power series. So, a power series is a series of this form. Sum. And we are going to start at n equals 0. Hello, n equals 0. Okay, please pay attention to that. C sub n, x to the n. This is a power series. So first thing I'll point out is that we have looked at this before. This is what the previous sections were about. Series where we had a bunch of numbers being added up, right? Now what we're throwing into the mix is that next to each number is a power of x. So let's start plugging in, let's write this out. If we plug in n equals 0, what would we get? C sub 0 times x to the 0, which is 1. So just c sub 0. All right, next one, we plug in 1, c sub 1, x. Next one, c sub 2, x squared, c sub 3, x cubed, and forever and ever, amen. Right? That's a power series. They call it a power series because it is a series, right, of powers of x, right? So it's a power series. Each of these c's, c sub 0, c sub 1, c sub 2, c sub 3, all of those are just constants. So I'm going to put here c sub j equals a constant for all j. So each of these guys is a constant. They could all be the same. They could all be different. All right? Just depends. So would you agree with this next statement? If we fix a value to x, then the series will converge or diverge. Do you agree with that statement? So if I tell you right now, hey everyone, x is 1, okay? X is 1. Then this is really not even here, right? And now you have a series from what we've been doing, right? Infinite series, and that's either going to converge or diverge. It's the sum of a bunch of numbers. If I fix x to be 2, then this is going to be a number plus a number times 2, plus a number times 2 squared, plus a number times 3 squared. But they're all just numbers, right? Added up. So again, that's just an infinite series of numbers, which either converges or diverges. Well, I don't know what it does, but it does one or the other. Yes? Okay. Let's look at a specific example. All right? Example. Let x be 1. Okay, so what would we get? Sum n equals 0 to infinity, right? And then we would have c sub n times 1 to the n, right? That's what it would be. Oh, I'm sorry. I'm doing this wrong. I apologize. My bad. Let me back it up. Back it up. That's not what I want to do yet. I got a little ahead of myself. Let c sub k be 1. Or c sub n. We'll use c sub n. C sub n be 1 for all n. What I'm doing is I'm saying, let's say that the constants in front, right, all those constants, let's say they're all the same all the time, they're always 1. Okay, then what does this become? Becomes 1 times x to the n, which is, do y'all see the difference here? I put the 1 here. I wanted the 1 on the c. So this is still a power series? Okay, so let's write it out. What would the first piece of this power series be? So 1 times x to 0, so 1 times 1 is 1, and then plus 1 times x plus 1 times x squared plus 1 times x cubed plus dot, 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 right? Do y'all agree? Now, do y'all remember what a geometric series looks like? What does a geometric series look like? What does a geometric series look like? It looks like a plus ar plus ar squared plus ar cubed plus, isn't that what it looks like? So couldn't you make the argument that what we're looking at right here is a geometric series with a being what? 1. This is geometric with a being 1. And what about r? R is x. R is x. And so will this power series converge or diverge? Will this power series converge or diverge? It depends on x, right? It depends on x. This right here will converge if what? This right here, this power series, will converge if the absolute value of x is less than 1, and it will diverge if what? Absolute value of x is greater than or equal to 1. Do y'all agree with that? Okay. So let me get this straight. Let me get this straight. If I define a function, and when I say let me get this straight, I mean let's us get this straight. Right now, if I were to walk up here and just write this on the board, I'm going to define a function, f of x. Right, here it is. I want this function to be the function 1 plus x squared plus x cubed plus x to the 4th forever and ever. I'm going to tell you, I'm defining a function this way. That is the power series we're talking about up there, right? Is this function well defined?
No. It keeps on going. It has a progression, but it keeps going to infinity.
So when you say a function is well defined, what do I mean by well defined?
I thought it stops at some point.
No.
Definitive.
When I say well defined, what we mean by that is if you start feeding it values, is it going to give you answers? Okay, so you have to be able to determine what the output is if you give it an input. So is this function a well-defined function? If you give it input, can it provide you with an output?
I mean, yes, but it's an infinite amount of output.
What's that?
Infinite time.
No, but I'm saying if I give you a value, like right now, if I ask you right now to plug in the value 2 into this, right? We just said that that's a geometric series, right? And it's going to converge to a number if the absolute value of x is less than 1 and diverge if absolute value of x is greater than 1. So if I feed it 2, what does this function do? It's infinite, which means it freaks out and it can't handle the number 2, right? So you give it an input and it goes, shit, I have to add this up forever, and that's infinite and it has no output, right? So guess what? 2 is not in the domain of this function. Just like if we were to come here and I wrote a function on the board, f of x equals the square root of x, you can't feed that number -1. Okay? Fine, -1's not in the domain. What can I feed this function? Give me a number I can feed it.
1/2.
1/2. I can feed it a half. And not only do I know that it's going to give me an answer, because that's a geometric series, I know the answer. The answer to this is a over 1 minus r, which is a half, which turns out to be 1 over a half. That's 2. So when I plug half into that function, it spits out 2. If I plug in a third, it's going to spit something out. This is a well-defined function. It's well-defined on its domain. What's its domain?
Anything below 1 or below.
Anything where the absolute value is less than 1. If you feed this thing any x where the absolute value is less than 1, then this function is well-defined and has outputs. Right? This is profound, okay? We have defined a function as an infinite series. Yes?
So 2 doesn't work because you said it goes to infinity?
2 doesn't work because this is a geometric series, and geometric series will diverge if this part right here, because the x is acting like the r, right? And the a is 1 in all of these. This is only one example, everyone, okay? This is just when the constants are 1. If these constants are not held at 1, we are not looking at a geometric series anymore. Everything changes. But for this specific example, which is an important example, that we're saying that this is true, right? This would hold. Now, check this out. This is kind of like mind-blowing the other way around. What does this converge to? What does this converge to if the absolute value of x is less than 1? What does it converge to? 1 over 1 minus the x, sorry, not the absolute value of x. That's what it is, right? Okay, so check this out. I really need the, let's turn the projector on. Can you turn the light on over there? top, not light, the top left, yep, hit that. And then the buttons, did it not come on? Yeah, that must be why the cart's in here. Damn it, the one day I'd really like to have that. Okay, oh well. It's not happening. All right, so this is what it converges to, right? If the absolute value of x is less than 1, it converges to this. Another way you can look at this is this. If I came into this class today and I said, hey everyone, see that function? Everyone would be like, oh yeah, from college algebra, that's a rational function. Great, whatever, right? Well, guess what? So long as you look at that function just between negative 1 and 1, okay? So graph that function and just look in there at that function. It will be identical to that. This infinite series, infinite power series, is equivalent to that function inside that little interval. Now, the problem is if you go on your calculator and try and graph this, you got to stop somewhere. So I challenge you, take it out to maybe the 10th power, graph these two things next to each other, and I bet you won't see the difference between the two. Okay. So, this is interesting, I think. Let's look at a different example.
So it would be geometric any time that c sub n equals like c?
If c sub n is a constant, right? If c sub n is always a constant the whole time, then it's going to be a geometric series. And therefore it'll converge so long as the absolute value of x is less than 1. Okay, now, just as you start to try and wrap your head around that a little bit, we are now going to define a general power series. Let me try and motivate this idea a little bit. You know how when I started this out, I said, hey, everyone, let's graph the cosine function and let's approximate it. And we said, okay, we can approximate cosine x versus this other thing, 1 minus x squared over 2. And I hope I convinced you that these two are pretty close to one another near what? Near 0, right? But what if I wanted to not be near 0? What if I wanted to be over here, like some value, let's say a? What if I wanted to be there so that when I plug in a here, this thing approximates it? Because right now, if I get too far away from 0, it falls apart, right? Yes? Well, all I have to do is shift my approximation. And do you remember in algebra how we shift functions left and right? We either add or subtract a inside the function, right? And it worked like if you add a inside the function, it moves it which way? Left, but if you subtract a, it moves it right. Inside the function. If you add a number on the outside, it moves it up and down. So a general power series looks like this. Sum n equals 0 to infinity, starting at 0. C sub n x minus a to the n. And this is the power series about a. That's the way we say that. The power series about a. So when I first introduced power series a couple of notes ago, what was a? That was 0, right? But now we're saying, hey, in more general terms, we can always subtract a in here. So what is that going to do? It's going to shift it. So if I wanted to know what was happening, like if I wanted to approximate what was happening at 3 here, then all I would do over here is what? I would use that instead. I would shift it to the right 3 by subtracting 3 on the inside of the function. Now I'm getting a little ahead of myself, but this is a general power series. Okay? Example. for what values of x does this power series converge? Sum n equals 0 to infinity, n factorial x to the n. All right, let's just kind of take a deep breath. This is a power series, right? The thing that makes it a power series is the fact that we have n equals 0 to infinity. We have x to a power, right? X to a power makes a power series. Then we have this thing out front, n factorial. That's our c sub n. That's our formula for getting the constants on each term. Just to kind of make sure we're all on the same page, let's just plug in some values and see what we get here. So we plug in 0, we get 0 factorial x to the 0, plus 1 factorial x to the first, plus 2 factorial x to the third, plus 3 factorial x to the third. No, what? Squared, sorry. 0, 0, 1, 1, 2, 2, 3, 3. Plus dot, dot, dot. That's what that is, right? Okay. Do y'all see that each of these constants in front of the powers of x are changing? They're different for each one. The previous example, the one that was geometric, was 1 the whole time. This is different. So this is not geometric anymore, okay? The question is, when does this thing converge? If I ask you to plug a value of x in here, is it going to converge or diverge? Right? For what values of x is this thing actually going to give you a convergent sum? So, how in the hell are we going to figure out if this series converges or diverges? Because it's not geometric, so we don't have this nice, cute little formula for it. Well, we're going to bring out the ratio test. Yeah, the one we just learned today. Okay, so what does the ratio test say? We need to take the limit as n goes to infinity of a ratio, right? Which is going to be this expression with what plugged in for n? N plus 1. So I'm going to write that down. N plus 1 factorial x to the n plus 1. And I divide that by what? That, right? Now, the reason I'm not doing that reciprocal thing is because I don't have a fraction to start, right? This wasn't a fraction to start. That's why I'm not writing a fraction and then the reciprocal next to it. It's just this with n plus 1 plugged in and then that. Okay. I want to know what happens to this as n goes to infinity, right? Let's see. Let's see what happens. Limit. We're going to do some factorial cleanup here, right? Do some factorial cleanup. We've got n plus 1 times n factorial, x to the n times x over n factorial times x. So I split this guy up, and I split that one up, right? Yeah, I forgot the n. I also forgot my absolute value bar. Does that make sense? Just cancel some stuff out. Sound effects are optional. Okay, there we go. So I've cleaned that up as best I can. And notice also I've separated the x here from the stuff with n's. Where did I get that n go? Where did that n come from? I was getting a little bit too excited there. My sound effects. Boom. Okay? Okay? Now, let n go to infinity. That's what I have to do right now, right? And what happens as n goes to infinity? That thing blows up, right? Times x. So let's think about this. What does the ratio test tell us? The ratio tells us if we take this limit and that limit is less than 1, we have convergence, right? If it's greater than 1, it's divergent. We're trying to figure out what value of x, for what values of x will this series converge. All we can control is x, right? It's like we're trying to figure out what the domain of this thing is. What x is going to make this thing not go crazy? And if you look at this limit, the only way to keep this less than 1, right? Because that's what it requires from the ratio test. The only way to keep this less than 1 is to do what? We only have control over x. So imagine right now you let x be 2. This thing's going to infinity, right? 2 times infinity, you're done. It's going to blow. It's going to be bigger than 1. It's going to diverge. If I let x be 1, still going to diverge, right? What's the only thing I can do to control this thing from blowing up? Let x be 0. That's it. If x is 0, we get convergence, don't we? If x is 0, that's not a limit, okay? This is not a limit. I'm not letting x approach 0. I'm saying let x be 0. If x is 0, this thing right here converges, right? Because you get 0 times infinity is 0 when that is identically the number 0, not approaching 0, right? There's a huge distinction here. So the only way to make this happen is it'll only converge if x equals 0 only. Right? That's the only way it's going to happen. Yes?
So x is not allowed to have n in its definition?
X is not allowed to have n in its
So like
definition.
x could equal 1 over...
That's right, no, because then it would be a constant. It would be part of the constant thing out front. So like if this x expression had n's in it, then you'd want it out here. Okay. So this is a weird example because what it's saying is like if you ever do this n factorial in front of x to this power, you try and come up with this power series, the only time this series actually ever makes sense and you can get an answer out of it is if you let x be 0. But if x is 0, it's a pretty boring function. It doesn't do anything. It can only take in 0 and it only spits out 0. So it's really, I still have 5 minutes.
The stuff I don't need.
Okay, so let's try this one. For what values of x does this converge? (2x minus 5 to the n over n). Is this a power series?
It could be. I think it's geometric.
No, we have x's in here now, right? We have x's, so we're in power series for sure. I'm going to write this as 1 over n times 2x minus 5 to the n. All right, that's kind of what we got here. Is there anything else I could do here? Because a power series has to look like this. Sum c sub n x minus a to the n. That's what a general power series looks like. So I'd really like to have that look like x minus a to the n. Not so much. We just need algebraically to make this look like x minus something. So
So it'd be x minus
pull a 2 out.
2.
Okay, be careful when you pull the 2 out though. So look, it'll be like this. Sum n equals 0 to infinity, 1 over n, and then we'll have, the 2 came out, right? And then you have x minus 5 halves, and then raised to what power? N. So what about that 2 to the n? Or this 2 right here being multiplied? I can do the n on that and the n on that, can't I? So that 2 to the n is a constant. It's controlled by n, but it's a constant. So I'm going to pop it out here with this. So this is going to become sum n equals 0 to infinity, 2 to the n over n times x minus 5 halves to the n. And now you have a power series. This is your C sub n, right? And this is your x minus a to the n. So this is a power series centered, centered, I haven't said that yet. I said a power series about A, right? You can also say a power series centered at A. It's centered or about is interchangeable. So this is a power series about the number 5 halves. So now what we would do is we would run a ratio test on that. And I am going to run out of time. I am out of time. So we'll have to stop there. We'd run a ratio test, and when we pick up next class, which will be next Monday, we will do another, we'll finish this one out. We'll do a Bessel function. Then we'll look at power series as functions. More examples. Radius convergence. We're getting there. We're getting there. So make sure, I'd say for your